There's one device that you would never, ever leave home without. We don't have to name it. You know what it is.
You could say semiconductors are the brains behind your smartphone. But new 2D materials could soon make high-tech devices even smarter, more nimble, and less visible. What if that same technology that exists in your smartphone could be implanted into anything on your body or in your environment? Instead of just having a smartphone, what if you lived in a smart world?
So now when we think about electronics, we think about devices, right? We think about our phones or maybe our smartwatches or smart glasses for those of us that might have those. But imagine if you could take an electronic device and simplify its task, to give it a sensor and to say, you're in charge of doing one thing for me really well. Well, you could put those sensors in just about everything in our world. So let's say I want to know, have I worked out enough today? How much have I sweat? I could put a sensor in a piece of clothing or a shirt and it could tell me that one thing. So imagine waking up in the morning, not knowing what to wear, putting on the one thing in your closet, and it's everything you need for the day. It gets hot, it gets cold, it protects you, it tells your doctor how healthy you are, and if you're like me and you really want to match your shoes, then it can even change color for you, depending on where you are.
Most materials are three-dimensional in that the connection between the atoms runs in all three dimensions, whereas in a two-dimensional material, the connections exist only within a plane, and so what you end up with are planes or layers of atoms connected together.
First group to actually isolate a single layer of atomic carbon, called graphene, was in England, the GIME group, and they did it in a very surprising way where they took a piece of graphite, which is actually billions of sheets of graphene stacked on top of each other, so you can imagine a stack of a sheets of papers, and they took Scotch tape and taped it to the top, peeled it away, and then repeatedly sort of bent the tape back and forth until they had a very, very thin layer of graphite.
What they ended up with is graphene, a single layer of pure carbon that's one atom thick. It's bonded together in a hexagonal honeycomb lattice. It's light and strong, flexible, and non-flammable. This discovery catalyzed interest in 2D materials.
So we're starting with this ultra clean surface of a germanium wafer, and we're going to go ahead and load this into what's basically a giant oven, and we're going to grow graphene on it from there. So let's get it loaded. And now once this outer chamber is pumped down, we'll open a door and slide the sample into the main chamber where the actual graphene growth will happen. So the sample is now making its way into the chamber, but we have to go very slowly to avoid risking dropping the sample. Keep coming. Okay, we close it. So now we're going to load a recipe, which we've carefully chosen the parameters of all the gas flows, the temperatures, and the pressures that we know will give us a good graphene growth. And we carefully ramp the temperature from 0 up to 920 degrees in this case to grow our graphene on germanium. So I'm going to go ahead and load this. It's one single crystal of graphene on a oxidized copper surface. So the white area, what you're actually seeing is in the white area, it's not oxidized. The copper isn't oxidized because it's protected by the graphene crystal. And everywhere else, it's sort of orangish, which is, as copper starts to oxidize, it turns to that color. So that's why we can see a single atomic layer of carbon in an optical microscope, because we're not actually seeing the carbon, but we're seeing how, by being there, it's protecting the copper from being oxidized. And this is several millimeters across, and it's a single crystal. So it's 1 atom layer thick and a couple millimeters wide.
Once upon a time, silicon was the king of semiconductors. In fact, they named a whole valley after it. But our need to make smaller and smaller electronic components has us looking at new semiconductor materials. Because graphene isn't a semiconductor, that's not the answer. But other 2D materials may be better posed to dethrone silicon as the ruler of the semiconducting world.
This is an atomic model of MOS2. And we can see that this is a layered structure when we recognize that there are groups of 3 layers that exist together. The yellow balls are sulfur and the gold balls represent molybdenum. And so it's a sulfur, molybdenum, sulfur arrangement. This is formal strong bonding, and then there's weak bonding that exists between the tri-layers. So one of the differences between graphene and MOS2 in thin film form is that the layers are going to be thicker. Because they have different atoms involved and there's different bonding, that also means that the energy levels are going to be different. Those differences in energy levels are what allow it to be used as a microelectronics device or incorporated into a transistor. Graphene and thin film MOS2 represent nanomaterials, and one of the defining characteristics of a nanomaterial is that its materials properties will change as a function of a reduction in size. And so in the case of these 2D materials, you have only single layers of atoms, or in the case of MOS2, you have tri-layers of atoms, and the reduction in scale to that point gives rise to unique properties. And that is true for electronic properties, for optical properties. Thermal properties don't change that much. With MOS2 being a nanomaterial, it calls for special tools to operate and study the material on that length scale. This is an ultra-high vacuum scanning tunneling microscope that allows the study of MOS2 in that way. The shiny stainless steel that you see is the chamber that houses the microscope, and the vacuum chamber nature of it is what allows us to prepare and clean pristine samples of MOS2 for characterization. The microscope is not an optical microscope, but a microscope based upon actually the electronic properties of individual atoms. By understanding how the electronic structure relates to specific structures within the material will allow us to tailor MOS2 to future microelectronics devices. That tailoring is involved in adjusting the energy difference between the electronic states that we've been discussing.
So microelectronics have evolved since the early 1970s. And one of the interesting things is that in 1970, there was a prediction by Gordon Moore that the number of transistors on a device or a chip would double every 2 years. And he had been plotting this up for a few years, and he noticed this trend. And what's amazing is that that trend has continued. And so that's what's called exponential growth. So today, for example, you have a modern, this is a wafer of silicon with each one of these 4 squares is 1 Pentium processor. So this is the equivalent of 350 laptop computers. On each one of these 4 squares now, there is 2 billion transistors. So the transistor is only 150 atoms across. In 2 years, there will be 4 billion transistors in that area. In 2 more years, there will be 8 billion transistors in that area. And this is what's meant by Moore's law. And so this has been a huge driving force for the semiconductor industry. They spend billions and billions of dollars every year trying to figure out how to double the number of transistors on each chip.
So what really excites me about 2D materials and their potential is that they can go where no materials have ever gone before, right? They're small, they're flexible, they're strong. We can put them on anything on our person and in our environment. What other kinds of things are we going to start relying on 2D-based technologies to do for us instead of us doing for ourselves? And sooner or later, are we going to become dependent upon these technologies in our lives? Will they start to tell us what to do instead of us telling them what to do? And what happens to human relationships in a world in which technologies are supposedly meeting so many of our human needs?
You're going to see it showing up in transistors, I believe, because of the unique electronic properties. But to be fair, we're not going to see it because materials that are only 1 or 3 layers thick in terms of atoms cannot be seen to the naked eye.
It's really funny because we always thought that digital technologies would make, and computers would make our lives easier and faster, right? We now have more friends than we've ever had before in our lives. We now have more information more quickly than we ever have before. And yet we seem more tired and more overworked than we ever have been before. And so there's definitely a risk that having more technology and more communication technologies in our lives on a daily basis could run the risk of wearing us out rather than helping us. So we have to think very seriously about where we want to use two-dimensional materials for electronics applications in our lives.
2D materials have the potential to build us a smarter world. How do we ensure that they serve us versus us serving them? An invisible material that's going to keep showing up. What we do with it is up to us.